Now I want to compare whether our dimensionless solution that we arrived at last time for flow between plates, sorry about that, compares to our former solution that was gotten using fully dimensioned terms. So we're going to start with our dimensionless solution to the velocity profile. So this is our velocity is a function of y across the channel and the flow between plates, and it's a function of the dimensionless y variable, the Reynolds number, and the dimensionless pressure gradient. And so how does that compare to the solution that we have where we use dimensional quantities? And I think I want to compare the average flow velocity, because that's the one we use the most, is average flow velocity and pressure gradients. So I'm going to define a new term, big U with a tilde, so I'll try to remember to write it big. Happily, I don't use it very long, so I don't have to remember very long. And we're going to try to calculate the average based on this. So the average, the big U, is equal to, of course, minus with a minus sign out in front here. And then we have 1 over the length of the channel. Well, in the dimensionless world, the length is only 1. So that's 1 over 1. So I wanted to include that. Obviously pretty silly, but this is the length of the gap, or the height of the gap. Sorry, I should say height of the gap. So we're averaging across the entire channel. So we're averaging from, in this case, dimensionless negative 1/2 to dimensionless 1/2. And that, of course, the total length there is 1. So we're putting that 1 down there in the denominator, and just to remind ourselves that we are averaging from minus 1/2 to 1/2. And then, of course, we have the dimensionless g, and the Reynolds number, and the 8, and the 1 minus 4 dimensionless y squared dy. So that's our average equation, and we can integrate that quite easily. The giant U, of course, I'm going to drop the 1 over 1. I'm just going to have a minus sign. The g and the Reynolds number and the 8 are all constants, so they just come out of the integral, and so they pull out here. And then I have the integral of this stuff in y, which is very clean and neat. Obviously, the integral of 1 is just y, and the integral of y squared is 4y squared is 4/3 y cubed, all with dimensionless. And then I have to evaluate that at minus 1/2 and 1/2. So there's my integral, okay? And I will evaluate that at minus 1/2 and 1/2. So I get my big U here, remembering still to write a really big U, so you guys can hopefully see that it's not little u. REH divided by 8. And when I plug in 1/2 there, I get 1/2 minus 4/3 of 1/2 cubed, which is 1/8. And then I subtract negative 1/2 and then negative 4/3, 1/8. So those are all going to add together, because both are going to become negative. Negative actually becomes positive, because it's a negative 1/2 cubed is negative, and then negative negative gives you the positive. So that's my integral. Obviously, I'm going to clean that up, add these terms together. So I'm going to have 4/24 there, and I have 4/24 there, which looks a lot like a 6. So I'm going to have the big U, here's my big U still, minus g, REH, my g is still dimensionless, 8, and then I have 1/2 plus 1/2 gives me 1, and I have 4/24 and 1/6, 1/6, so that's going to be minus 1/3. So that gives me minus 1/3, and so I end up with big U here is minus g REH over 8 times, that would be 2/3, right? So 2/3, and of course 2/3 of an 8th, that gives me 2/24, and 2/24 is a 12. Minus g REH over 12. So that's my solution for the average flow velocity. So this is average flow velocity in the channel. So we want to see if that matches what we had before. So this is our new solution based on the dimensionless parameters. Sorry, this is dimensionless as always. right now. So that's my dimensionless parameter, dimensionless pressure gradient. Obviously, the Reynolds number we know is dimensionless, a dimensionless average velocity. So we're going to try to see how that compares to our dimensioned answer. Now, our dimensioned answer was u bar, the average velocity, was equal to the pressure gradient, h squared over 12 mu. So if you look back at your notes, you'll see that that was the average velocity for flow between two plates that we arrived at using basically the same technique. But now we're going to see how that compares to this. And we can see there are certainly similarities, but they definitely don't look exactly the same. There are definitely differences, and hopefully those differences will resolve. So the way we're going to explore that is I'm going to turn my dimensionless quantity back into a dimensional quantity. So to do that, I need to define all of these terms. So I have the dimensionless velocity, the dimensionless pressure gradient. The dimensionless pressure gradient has dimensionless pressure in it. The pressure dimensionless was rho u infinity squared. So that's the p over rho of u infinity squared is dimensionless p. And dimensionless x was x over h. So I have constants coming in there. That's going to give me, if I pull those constants out, I have dp dx, which are the variables. And then I have the constants that come out are 1 over h and 1 over rho u infinity squared. So they're going to go there. Obviously, they're both in denominators, so they're going to pop and flip. So I have that the dimensionless pressure gradient is equal to dp dx times h divided by rho u infinity squared. So that's going to be my relationship there. And now I'm going to plug all this stuff, plug this into there for my my pressure gradient, and I'm going to plug in this stuff into here for my dimensionless velocity and see how I do. So let's see how that works out. So that's what I'm plugging in. I'll leave it where you can see it a little bit. So on the left-hand side, I've got the u bar over u infinity, replacing that u tilde. And then I'm replacing the g with dp dx h over rho u infinity squared. And then I've got the Reynolds number, which I'll leave for the moment. And then I got this 12 hanging out. And I got a minus sign. So that looks okay. Now I'm going to obviously solve for u bar. So u bar stays on the left-hand side. Multiply u infinity over to the right. I've got minus dp dx. I've got I've got h over rho. I've got an h over here. I've got 12. I'm going to put the rho in the denominator. I've got u infinity squared times u infinity because 1 u infinity is coming over. So I've got 1 u infinity up here. And I've got my Reynolds number based on h. Now I'm going to plug in for my Reynolds number, minus dp dx. I've got h over u infinity, all over 12 rho. But I've also got u infinity h over nu. H's are going to multiply each other. So I've got u equals minus dp dx h squared, u infinities cancel each other, divided by 12 rho, and this nu comes in the denominator. So I've got u bar is equal to minus dp dx h squared over 12 rho times nu is mu. So that is exactly the same as what we said was our solution for the dimensional solution, which I had somewhere here. But anyway, it was this. And so we see that we do, in fact, get the same answer. Oh, here it was. It was written right here. I didn't put a box around it. So g minus g, which is dp dx, minus g. We got h squared. We got 12. We got mu. So they come out to be the same. So that's great. So at the very least, we have learned that we can choose to use the dimensionless technique we will get the same answer, at least for the average flow velocity. Of course, you get the same answers for all the velocities. The whole point is you can work in dimensions, or you can work dimensionlessly, and you get the same answer. So now we'll talk about how you would really use dimensionless to solve a real problem, and then we'll talk about what its advantages and disadvantages are.